Hello, everyone, and welcome to The Explainer. I am absolutely thrilled you're here today because we are embarking on a masterclass covering something we all use every single day, yet honestly rarely stop to truly understand. So let's just dive right in. Today, we're unpacking the anatomy and the soul of modern computing. We're going to virtually peel back the metallic case of your laptop and the glass of your smartphone to figure out exactly how these machines actually work. We'll start from the physical hardware and go all the way up to the invisible magic of binary data. Just think about this for a second. How in the world did humanity go from ancient Babylonian counting tools, literally unbaked clay spheres used to count sheep, to coin-sized microchips that can process billions of calculations per second using nothing but ones and zeros? It's just an incredible journey of human ingenuity, and by the end of this explainer, you're going to understand exactly how that massive leap happened. So here is our roadmap for today. First, from abacus to microchips. Second, the anatomy of hardware. Third, how computers represent data. Fourth, the power of software. Fifth, transforming our modern world. And finally, the future of computing. Okay, section 1, from abacus to microchips. To really understand how a computer works, we first have to understand why we even needed them in the first place. You see, computing isn't a new idea. It's a super ancient pursuit. We humans have always needed help calculating things. Way back, around 100 BCE, we had the Antikythera mechanism in ancient Greece. This was an incredibly complex analog device with gear wheels used to calculate astronomical positions. Fast forward a bit to 1833, and the English polymath Charles Babbage conceptualizes the analytical engine. This was actually the first design for a programmable mechanical computer which used punched cards for input. Then World War II acts as this massive catalyst, bringing us to 1945 with the ENIAC, the very first fully electronic, programmable, Turing-complete computer. And that incredible lineage brings us right to today, where all that immense power is condensed into a coin-sized system on a chip, or SoC, living right inside your phone. Let's actually pause on that 1945 ENIAC computer for just a second, just to give you a sense of scale. 30 tons. That is how much the ENIAC weighed. It used 18,000 vacuum tubes and sucked up 200 kilowatts of electric power just to do a fraction of what your digital watch can do today. Imagine a machine taking up an entire large room, requiring operators to manually unplug and replug thick cables just to run a new calculation. It truly creates a sense of awe when you compare it to the tiny, hyper-efficient devices we carry in our pockets. So how on earth do we shrink 30 tons of machinery into something that fits on your fingertip? That brings us to section 2, the anatomy of hardware. A general-purpose computer really relies on a few main components working together. Let's contrast the two biggest players here, the central processing unit, or CPU, and computer memory. Think of the CPU as the brain of the whole operation. It houses the arithmetic logic unit, which executes the math and logic, and a control unit that manages all the signals. But, well, a brain needs a place to store its thoughts, right? That's memory. Random access memory, or RAM, acts as this temporary super-fast workspace for data and instructions that are currently being used. Meanwhile, read-only memory, or ROM, holds the permanent essential startup instructions. Basically, the CPU is constantly fetching data from memory, processing it, and sending it right back. But here is the real secret to how everything got so small. It's the transistor, specifically the MOSFET. That stands for Metal Oxide Silicon Field Effect Transistor, invented back in the late 1950s. At its core, a transistor is simply a microscopic electronic switch. It entirely replaced those massive, hot, fragile vacuum tubes they had to use in the ENIAC. Because MOSFETs are highly scalable, engineers eventually figured out how to cram thousands, then millions, and now billions of these microscopic switches onto a single piece of silicon to create an integrated circuit. This tiny little invention is the driving force behind the entire microcomputer revolution. Moving right along to section 3, how computers represent data. This is where it gets really fun. Remember those microscopic switches we just talked about? Well, here is the most fundamental rule of any digital computer. Everything, and I mean absolutely everything, boils down to a single switch called a bit, which is just short for binary digit. I want you to picture a simple, everyday light switch on your bedroom wall. It can only ever be in one of two states, right? It is either switched on, which the computer reads as a 1, or it is switched off, which the computer reads as a 0. There is no kind of on or mostly off. It's a strict binary choice, true or false.
1 or 0. This incredibly simple on-off state is the entire foundation of digital data representation.
Now, one single switch on its own is, frankly, pretty boring. It can only count to 1. But what if we line up 8 of these switches in a row? In computer science, a group of 8 bits is called a byte. If we flip all 8 of those switches to the on position, so 1, 1, 1, 1, 1, 1, 1, 1, using the rules of binary math, the computer reads that sequence as the decimal number 255. So with just 8 switches, we suddenly have a range from 0 to 255. But wait, what if we need to do math with negative numbers? Well, computer scientists came up with a clever rule called 2's complement. We essentially sacrifice the very first switch in that row of 8 to act as our plus or minus sign. If that first switch is on, the number is negative. That simple trick allows us to represent a range from negative 128 to positive 127. It's almost like a fun secret code, where flipping switches allows us to build literally any number we want.
And here is the absolutely crucial takeaway. If information can be represented numerically, a computer can store it. This is the real magic trick of computing. An uppercase A on your keyboard, it's assigned a specific number. A tiny pixel of the color red in your favorite photograph, assigned a specific number. A sound wave in a song, sliced up and assigned specific numbers. All of those numbers are then translated into those sequences of ones and zeros, those groups of bytes, and sent to billions of microscopic physical switches to be processed by the CPU. And that, my friends, is how data representation works. All right, section 4, the power of software. So billions of microscopic switches sitting in a memory bank are cool, but they don't do anything on their own. They need instructions. Software is the immaterial, encoded information that essentially acts as the soul of the machine. The big conceptual leap for software came from the brilliant mathematician Alan Turing in a seminal 1936 paper. He proposed what he called a universal computing machine. You see, before this, machines were built to do one very specific task. If you wanted the machine to do something else, you literally had to physically rebuild and rewire the whole thing. Turing realized that if the instructions for computing were just numbers themselves, they could be stored right in the computer's memory alongside the data. This stored program architecture meant a single physical machine could perform any task imaginable simply by swapping out the software program loaded into its memory. It was a real game changer. So how does the CPU actually read this software? Well, it uses a continuous loop called the fetch, decode, execute cycle. Step 1, the control unit reads or fetches the next instruction from memory. Step 2, it decodes that numerical binary code into control signals. Step 3, it executes the instruction, often sending it over to the arithmetic logic unit to do the heavy math. And finally, step 4, it increments a special register called the program counter to point to the next instruction in line. I always like to compare this to a human reading a book. You read a sentence, you decode its meaning in your brain, you react to it, and then your eyes move to the very next sentence. A computer does this exact same sequence just billions of times per second and without ever making a mistake. Section 5, transforming our modern world. Now that we know how the hardware and software work together on this microscopic level, let's zoom back out. How do these billions of binary calculations per second actually impact our daily lives? Well, in the business world, computer systems are the absolute backbone of modern operations. They automate the routine, tedious tasks that used to take human clerks weeks to complete. They optimize massive global supply chains, tracking inventory all the way down to a single item on a shelf. They allow for incredible business intelligence, taking mountains of complex data and analyzing it to spot market trends and financial opportunities. And they enhance customer support, allowing for seamless online transactions and highly personalized marketing. A modern business today simply cannot survive without leveraging these systems. And the impact on education has been equally revolutionary. We have moved so far beyond the days of outdated physical textbooks. Computer systems give students and educators access to virtually limitless digital libraries and global online resources. They allow for interactive multimedia learning, where complex scientific concepts can be visualized in stunning 3D. Students can even run virtual experiment simulations that would just be too dangerous or way too expensive to do in a physical lab. And ultimately, this all teaches digital literacy, things like coding, computer science, and data analysis, which are absolutely vital, non-negotiable skills for success in the 21st century. But perhaps the most profound impact of all is in healthcare, where computer systems are literally saving lives every single day. They securely manage electronic health records, meaning doctors always have your complete medical history instantly at their fingertips. They process the staggering amount of data required to generate advanced MRI and CT scans, allowing for super precise, non-invasive diagnostics. We even have computer-assisted robotic surgeries that can perform delicate procedures with a level of microscopic precision human hands just simply can't match. And today, AI and machine learning algorithms are actively analyzing vast medical datasets to predict disease patterns before they even emerge.
Finally, Section 6, the future of computing. It really is breathtaking how far we've come. But you know what? The journey isn't over. Two massive frontiers are opening up right now that show us exactly where this technology is heading next. On one side, we have quantum computing. Instead of classical bits that are strictly a 1 or a 0, quantum computing harnesses the mind-bending laws of quantum mechanics. It allows for processing power so immense that it could solve complex global energy or chemical challenges that are currently completely impossible for classical computers to crack. On the other side, we have the Internet of Things, or IoT. This is the massive push to embed microchips and sensors into everything, connecting billions of everyday items from your kitchen refrigerator to city traffic lights, creating a massive interconnected smart grid of data.
And that leaves us with a truly profound thought to end on. We started this explainer looking at ancient, unbaked clay counting spheres. Today, we have engineered silicone all the way down to the atomic level, and we are teaching machines to learn and predict via AI. As quantum mechanics pushes us beyond those simple binary ones and zeros that have defined computing for the last 80 years, what previously impossible human challenge will computers solve next? Will it be climate change? A cure for cancer? The limits are bound only by our imagination. I really hope this explainer gave you a deep appreciation for the incredible machines sitting right in front of you. Thank you so much for joining me on this journey today. I encourage you to keep questioning, keep learning, and keep exploring the absolutely amazing world of computer science.